In spring 2006, I took Fundamentals of Modern Math with Dr. Coverley at the University of Tulsa and Advanced Calculus 1 with Dr. Redner. Those two courses changed the trajectory of my life. Because of those courses, which were my first introduction to theorem-proving, I decided I wanted to stop studying psychology and devote myself to learning math, studying these beautiful mathematical structures, which described relationships between beautiful mathematical objects. And I wanted to apply this reasoning and use this reasoning in other areas of my life and teach my students to do the same. So that's what this video is about. This is the first video, hopefully in a series of many, about logic and proofs. My goal is to explain to you why you should study advanced math and what you should expect to learn in a theorem-proving class. At least just a taste of it. And it's all based on this book, Transition to Advanced Mathematics. I'm going to use the 6th edition, which I have right here. This is the book I learned out of in spring 2006. The 8th edition is available online. I'll choose some problems for us from that textbook as well. So why study advanced math? The short answer to that question is math is about learning to think for yourself. We're not memorizing facts, although we are memorizing definitions and learning definitions and learning theorems and learning how things work. But it's really not about memorization. It's about taking some known information, typically from a problem statement, and figuring out what we don't know and figuring out what we want to know and figuring out, whether or not we can get what we need to know from what we already know. And if we can't, we go look it up in a book, we find another resource, and we figure out what we need to know in order to solve this question. And then we just try to get from point A to point B. We take everything that we know and we use it to figure out what we want to know. That's critical thinking. That's problem solving. And that is a skill that will help you in every aspect of your life, whether you're talking about your relationships or how to get your car fixed or how to solve any problem in your life. The ability to dissect that problem, figure out what's important, ignore what's not important, use the information that you have to get the information that you want, is just a wonderful skill. That's critical thinking, and that's what mathematics will teach you. Now, in high school math and in beginning college level math, like calculus 1, 2, 3, and differential equations, we're typically solving textbook problems. So the problems are well posed. Most of the problems have answers. If the problems don't have answers, we sort of already know the types of cases that we'll see where the answers, maybe a solution doesn't exist, or when we have infinitely many solutions or something like that. But all of that is sort of outlined for you. And usually you're looking at specific cases and you're trying to find out a particular result. You're trying to maximize the cost. You're trying to find the length of that side of a triangle. You're trying to find the direction of steepest ascent or the direction of steepest descent in a calculus class. All of those things are very important and very useful. But when you go to the advanced mathematics classes, the theorem-proving classes, like the one that we're about to start here, we're doing something very similar in the sense that we are starting with some things that are known and we're trying to figure out what's unknown. We're trying to figure out the implications of those facts and those ideas that we started with at the very beginning. But rather than applying that process to something that's very specific and trying to find a maximum cost, for example, now we're going to do this in a much more general way. And as we do this in a much more general way, we're going to be learning about properties, beautiful properties of mathematical structures. And we often strip the details away so that we're not really interested in whether we're looking at a matrix or a polynomial or a set of real numbers or a set of complex numbers. If, let's say, for example, if we know that set forms what's called a field, or that set forms what's called a ring, or that set forms what's called a group, we know a lot about those. So what we're going to do instead in a theorem proving class is we're going to take what we know and we're going to think about all of the logical implications of what we know. But rather than applying it to a specific problem, we're going to apply it to these beautiful mathematical structures, which are so general that they apply to many things. And we'll talk about more about that in a little bit. Now, there are two different types of reasoning that are typically used. We use inductive reasoning and deductive reasoning. And deductive reasoning is the type of reasoning that I'm emphasizing here, and that the type of reasoning that you'll be using in a theorem proving class. But let's distinguish between the two before we go on. Inductive reasoning is the type of reasoning done in STEM. Now, mathematicians use both inductive and deductive reasoning, but when we think of the sciences, we tend to think of inductive reasoning. So basically what they're doing is they're taking a bunch of observations, and sometimes they're taking observations that are the result of experiments, but primarily observations. And they're saying, based on those observations, based on that pattern, I have a theory. I think that this is how things behave in general. And so they'll come up with some theory, and then they'll test that theory by running experiments. They'll say, if my theory is true, then I should be able to run an experiment, and that experiment should show, that something else is true. And so they're verifying that their theory is true, by experimenting. Now, the downside of inductive reasoning is that if you use this process, one new observation that contradicts the theory means you need to throw the theory out. It means the theory is wrong. Now that can hurt. You might be kinder to yourself and kinder to your colleagues and say, the theory is not wrong. Maybe the theory is incomplete. But usually mathematicians and scientists are not offended by a theory being wrong. They're intrigued by it. They find it tantalizing and intriguing when you realize that this theory is lacking in some way. You say, how must it be how must it be modified? What do we need to do so that all of the observations that we've seen so far are described well by this theory? This is a picture of Marie Curie. I'm a huge fan of Marie. She was a physicist and a chemist. You probably know that she won 2 Nobel Prizes for her work in radioactivity. She's kind of a rock star in the STEAM sense. But she was using inductive reasoning when she made observations and took note of those observations and used those observations to come up with a theory and then confirmed her theories by experiment. Now, in math, we tend to use what's called deductive reasoning. This woman is also a rock star. She's amazing, or she was amazing. She's no longer with us. We lost her to breast cancer a few years back. Her name is Miriam Mirzakhani. I apologize if I'm mispronouncing her name. She won the Fields Medal. She's the first female to win the Fields Medal. She's also the first Iranian to earn the Fields Medal and the first Muslim to earn the Fields Medal. Not that all of those identity groups matters. That's really not what it was about. She was just amazing, an amazing human being who happened to be extraordinarily talented and win the Fields Medal for her outstanding work. She was interested in geometry of Riemann surfaces, as described here. Now, in this image, Miriam is probably teaching a class, and she may not be talking about deductive reasoning. She may not actually be writing a proof, although she might be teaching her students how to write a proof about these hyperbolic surfaces that we see are described on her whiteboard there. But she tended to use this process of deductive reasoning whenever she came up with a proof of some result. So this is how it works. When you're using deductive reasoning, you start with what's known. You start with axioms, truths, known results, something that we can sort of grab onto, and we're absolutely sure is true. And then we're taking those truths and we're applying logic to those to construct what's called a proof. And then on the basis of that logic, which was based on the axioms, we're coming up with new truths. And we usually call those new truths theorems. Sometimes we call them lemmas. But the idea is that we take what we know to be true, and then we use sound logical principles that we'll talk about through this series of videos in order to come up with new truths. Now, again, as opposed to a problem that you might solve in a pre-calculus class or a calculus class, the goal, the new truth that you're trying to find is often unknown. There might be some exploration, or the new truth that you're trying to find might be some conjecture that you came up with using more of an inductive reasoning approach, where you noticed a pattern in some numbers, or you noticed a pattern in some structure, and you said, I think this is what's going on. And so you stated what you thought was going on, like a theory, and you tried to prove it. But what's different about this, as opposed to the inductive reasoning, is that with the inductive reasoning, the scientists are coming up with a theory, and then they are testing it with experiment. So they're saying, okay, if this is true, then if I do this experiment, then I should see this result. But experiments don't prove that anything is true. Experiments provide evidence. So when I think of inductive reasoning, I think of somebody looking at evidence, coming up with a theory of what's going on, testing that theory, and saying all the evidence suggests, all the available evidence suggests that this is true. So I'm going to stick with this theory. I think that's the truth. Now, with deductive reasoning, it's not based on evidence, it's based on proof, it's based on sound logic. So the beauty of this is that when a mathematician is right, and the axioms that we started with were right, and the reasoning was sound, we get to be right forever. There's not going to be some additional observation that tells us that we should throw our proof out the window, the way scientists might have to throw a theory out the window. When we're using deductive reasoning, we get to be right for all time, which is kind of cool. So math is what I would say is an art and a science. Again, we use both inductive reasoning and deductive reasoning. We're using inductive reasoning whenever we recognize patterns, whenever we see patterns and we try to describe them, when we see relationships between objects and say, huh, isn't that interesting? I think this is what's going on. Then we're using that inductive reasoning. But the difference between, again, a mathematician and a scientist is we're not going out into the world and observing things and collecting evidence. Rather than collecting evidence, we're going to use this process of deductive reasoning to prove something must be true. And what's interesting about this is that as you're writing the proof, as you're constructing it, I mean, sometimes you can use brute force methods, but most of the time, the proof itself is really insightful. It tells you why something is true, because it tells you, how these objects are sort of interacting with each other and how they must be related to each other on the basis of logic. And that is what I fell in love with in Dr. Coverley's class. I thought that was really beautiful, and I loved the creativity in it. We could use any method that we wanted to try to get from P to Q, the thing that we have assumed to the thing that we want to show. And that was really fun and really interesting. So that's what we're doing whenever we're constructing a proof, is we have some conjecture, the result of some inductive reasoning, and we're saying, okay, how can I prove that this is true all the time? And that's the deductive reasoning. I've been using this word proof over and over, and I haven't even told you what it means. A proof is a complete explanation of why something must be true. So for emphasis, it tells us what must be true. It tells us why it must be true as well. Now, there are many reasons to prove theorems. Again, one of the reasons is that when we're using deductive reasoning, as long as the axioms that we started with were actually true, and our reasoning was flawless, and it ought to be, we get to be correct forever. So I found this image online. It was like, yes, I'm always right, or we're always right. Let's be more inclusive. This is a club of people who are comfortable with logic. And I'll tell you, it feels good. It feels good to be correct about some assumptions. Now, I'm sure other scientists in other fields, they feel the same way when the evidence supports their theory about how things work. But again, it's the difference between evidence supporting something and proving something. And I'm all about the proof. Evidence supporting something is great and valid and important. But how wonderful is it to use sound logic to get to something that's true all the time? So that's one reason to prove things, because when you're correct, you get to be correct forever, which is pretty cool. Now, this is just another slide showing you the difference between inductive and deductive reasoning. With inductive reasoning, we start with some observations and we come up with theories and laws, and then we seek more evidence supporting those theories and laws through experiment. With deductive reasoning, we start with some axioms or assumptions, and we say, okay, well, if those are true, then what must be true based on that? And we come up with a truth, and we come up with a truth and another truth. We typically call those truths theorems, or if they're not really that big a deal, they're just sort of an intermediate truth, we call them a lemma, but they're true all the time. Now, these funnels may not be the best illustration, because when you're using deductive reasoning, it doesn't feel like you're funneling out to all of these possible truths from the axioms. You're usually just focused on one truth at a time. So you start with what's given, and you're trying to get from P to Q, or you're trying to get from what's given or what you know to what you want to know. But in math, we tend to do that lots of different times as we prove lots of different things, and sort of the texture and fabric of this mathematical structure we're studying, which describes particular mathematical objects, it just becomes richer as we unravel all of the truths that stem from those original assumptions or the original axioms of some system. Now, playing the devil's advocate here, there might be some students that say, well, can't we just use trial and error? But again, the problem with trial and error is what you are getting with trial and error is evidence that something is true. And there's a difference between evidence and proof. We can't use trial and error because there are statements out there that may be true a lot of the time that aren't true all of the time. And mathematicians are not happy with things that are true a lot of the time. They want to be right all of the time. And that makes us sound really bad. I don't mean it to sound that way. Basically, we want our conclusions to be sound. And what you'll find is if you're proving something, often in order to get to some results, in order to prove that something is true, what you end up with is a lot of qualifiers. So as you're going through the proof, as you're writing, you'll see, okay, I'm stuck here, I'm stuck at this level. I have to assume that this is something in order to keep going. So you'll say, okay, assume that that function is of exponential order, well, then math's gonna go to 0 and I'll be able to keep going. And so you, just for example, so you make the necessary assumptions so that you can get to some results. And what that does for us is that when you're done, you will know all the necessary assumptions to get to that result. And those assumptions are insightful. You'll know that if this is true and this is true and this is true, then I am guaranteed, as long as my logic is sound and my truths at the beginning were actually true, you're guaranteed that that final result is true. We're not happy with evidence, we want proof. That's pretty much the short answer. And trial and error will never give you proof, it will only give you evidence. So here's a statement that you might want to prove with trial and error. True or false, the square root of a squared plus b squared is equal to a plus b. Many a calculus student wants to do this. They might see, maybe in the trigonometric substitution section, the square root of x squared plus 4. And they might say the square root of x squared plus 4 is x plus 2. Just take the square root of the x squared, you get x. Take the square root of the 4 and you get 2. So it must be x plus 2, right? And they're not really sure. They're not experts at algebraic manipulation. They really haven't done that much algebra yet. And now it's in the context of this calculus 2 problem, and maybe they haven't simplified an expression like that in a while. And they're not 100% sure whether or not this is true. One way that you can test whether or not this is true is to just use trial and error. And as long as you use enough examples and enough diverse examples, the trial and error method will work well. Before I go on, I know I'm giving it away, but I just wanted to emphasize this statement is not actually true. This is an alternative fact in the sense that it's not true. And we don't want to try to apply this alternative fact to anything. Please don't do that. Your calculus teacher will be very mad at me if you try to apply this alternative fact. But let's prove that it's not true. Let's prove that it is false at least some of the time through trial and error. So let's see. You might plug in A equals 0 and B equals 5. You might say, okay, when in doubt, when you have an equal sign with a question mark above it, I should have put a question mark there. You might say, well, let's just plug in some numbers and see what we get. And again, this is providing evidence. This is more of an inductive reasoning approach as opposed to a deductive reasoning approach. We're just trying to figure out, whether or not we can do this, whether or not this is legal in, let's say, a calculus class when you haven't been in algebra in a while. So you might plug in A equals 0 and B equals 5. If you do that on the left-hand side, you'll have the square root of 0 squared plus 5 squared. 0 squared plus 5 squared is 0 plus 25. 0 plus 25 is 25. And the square root of 25 is 5. So the left-hand side turns out to be equal to 5. The question is that the same as the right-hand side? Well, if I plug in A equals 0 over here and B equals 5, I get 0 plus 5, which is 5. So the left-hand side is 5, right-hand side is 5, so 5 equals 5. Does that mean this is true? It means it's true when A equals 0 and B equals 5. It doesn't mean it's true all the time. And the context that's implied by this is that we want to know if it's true all the time. Can I always do this? Is this okay? Pick some other numbers. So let's pick A equals 3 and B equals 4. If A equals 3 and B equals 4, if we substitute A equals 3 into the left-hand side and B equals 4 into the left-hand side, we've got the square root of 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, the square root of 25 is 5. Question is that the same thing as 3 plus 4? 3 plus 4 is 7. So the left-hand side is 5 and the right-hand side is 7. So that is what we call in math a counterexample. That is an example of why this is not true all the time. Now you might wonder to yourself, okay, is it true some of the time though? And one way that you could prove when it's true some of the time is by squaring both sides and then sort of throwing out any extraneous answers. It turns out that this statement is true when one of those numbers is 0 and the other one is either 0 or positive. So if A is 0 and B is some number that's non-negative, meaning it's 0 or positive, then the square root of 0 squared plus B squared will be the square root of B squared, and the square root of B squared will be 0 plus B. It'll just be B, as long as B is non-negative. And of course, B could be 0 and A could be non-negative instead because they're basically playing the same role. This is sort of symmetric in that way. There are conditions, there are times when this is true, but it's not true all the time. And we can sort of guess over here, just try the trial and error method. And as soon as we find one counterexample, that's enough for us to say the whole statement is false. If we're trying to say that it's true for all A and B, all real numbers A and B. But if we're interested now in saying, okay, well, we know it's not always true. When is it true? We have more work to do. And for that, we might use some algebraic manipulation and some deductive reasoning. Now, just before we go on to any other example, I want to emphasize that this is not a fact. This is not true. So please do not take the square root of x squared plus 4 and tell somebody that it is equal to x plus 2 because it's not. Here's Nancy Reagan. She says, just say no to this. Friends, do not let friends make this algebra error. Do not do this. Square roots do not distribute over addition. You can't just take the square root of this guy and the square root of this guy and add them together. It doesn't work that way. So please don't make that error in your calculus classes. That is not a fact. That was false. That statement was false for all numbers. And it turns out that it's true when one of them is 0 and the other one is non-negative. Okay, so again, why can't we just use trial and error? Because a state just, and this is why, because a statement that might be true a lot of the time is not necessarily true all of the time. We can't use trial and error because a trial and error gives us evidence, and we don't want evidence. We want to be right. We want to be accurate. We want proof. Evidence and proof are two different things. Scientists are okay with evidence because they're studying the natural world. But we're studying these abstract objects, these abstract mathematical objects, and it turns out that we can prove a lot of things if we know some, other truths, if we have some assumptions that we're allowed to make, that we're allowing ourselves to make. So we prefer proof, and that's what deductive reasoning is. Now let's look at another example. Oh, but before we do the other example, this is just a list of some familiar sets of numbers. The ones that are most important to us here are the natural numbers. The natural numbers are represented by this n with the double bars, and they're just the counting numbers, 1, 2, 3, 4, 5, and so on. If I wanted to, I could keep going, and I would be here all day, and I would be here forever. I'd have to take breaks to eat, but it just goes on and on forever. Those are the natural numbers. Below that, we have the natural numbers. If we add 0 to that list, those are called the whole numbers. If you take all those numbers and then you add the opposites of the natural numbers, those are called the integers. That's represented by this z with the double bars. And then we've got the rational numbers and the real numbers and the complex numbers. And those aren't necessary for our presentation today. But these are just some shorthand ways of representing these sets of numbers. So Q is the set of all rational numbers, and rational numbers are just numbers that can be written as an integer divided by an integer. Of course, the denominator can't be 0. Okay, now in order to prove the next result, we need two definitions. One is A divides B. For natural numbers A and B, so we're talking about two natural numbers, 1, 2, 3, 4, 5, we've got two of them. We say that A divides B if and only if there is a natural number K such that B equals A times K. Or in other words, A is a factor of B. Whoops, I went a little too fast. We also need the definition of a prime number. A number P, a natural number P is prime if and only if P is positive. And the only numbers that divide P are 1 and P. So just as an example, since 10 is 5 times 2, we say that 5 divides 10. We also say that 2 divides 10 because 5 and 2 are factors of 10. To give you an example of a prime number, 13 is prime. The only way that you can write 13 in a factored form is to say 13 times 1 or 1 times 13. Those are the only two ways. 10 is a product of two prime numbers, 5 and 2. Of course, you could multiply by a 1 as well, but that's not the point. The point is it has two factors that are prime. 13 only has one prime factor. So again, then a natural number P is prime if and only if P is positive, and the only numbers that divide P are itself and 1. Okay, so with that in mind, let's go back to this question over here. Let's say we're saying to ourselves, true or false? N squared minus 3n plus 43 is prime for all positive integers n, or for all natural numbers n. So the question is n squared minus 3n plus 43 always prime? That's what they're asking us. I mean, they're saying, is that true? Or is it false? One definition I didn't put up there was composite. A natural number is composite if it's not prime. Okay. So let's say you're trying to use that brute force method. You say, I just want to check out the evidence. And it's actually a really good way to start. You might plug in some values for n and see if you notice any patterns. So let's plug in n equals 1. If n is equal to 1, we've got 1 squared minus 3 times 1 plus 43. 1 squared is 1. We're subtracting 3. 1 minus 3 is negative 2. Negative 2 plus 43 is 41. And if you check a list of primes, you find out that that is prime. So you'd say, okay, Well, I know it's at least it's prime when n equals 1. What about when n equals 2? You do that calculation and you also get 41. Say, huh, that's prime. 3, that's prime. 4, that's prime. You might just keep going. And guess what? For n equals 1 through n equals 10, all of the results are prime. And so you might be tempted to think that this is prime all the time. And so you might keep going. And you're going to be there for a long time. It took me a while just to make this slide because I was just typing this over and over and over again, changing the numbers, changing the red numbers. Look, they're all prime. Prime, 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 prime. Wait, stop. When n is equal to 43, we end up with this composite number. It's composite. So it turns out the statement is false. Now, if I was looking for evidence that n squared minus 3n plus 43 is prime, there was a lot of evidence at the beginning. N equals 1, n equals 2, n equals 3, n equals all the way through 42. All of those numbers resulted in a prime number. But turns out when you plug in n equals 43, we get a composite number. Now, this brute force method is obviously not the best way to go. It's the trial and error method. Now, if this statement happened to be true, let's say that n squared minus 3n plus 43 was actually prime for all positive integers n. I could have kept going forever. And I never would have proven that this expression is prime for all positive integers n, because there's always the chance that the next value of n is going to give me that composite number. So I can't prove this is true using trial and error. I would have to be able to try every possible value of that positive integer n, every possible natural number. And since I can't try every possible natural number, I wouldn't be able to prove that this way. There is a way that I could prove that using something called the principle of mathematical induction, and we'll talk about that a little bit later. But trial and error would never get us there, because there's always the chance that that next observation will contradict all the previous evidence. So we had overwhelming evidence that this was true, and it turned out to be false. Now, there's a better way of going about solving this problem, deciding whether or not n squared minus 3n plus 43 is prime for all positive integers n. Here's a more insightful approach. You might say to yourself, okay, I'm wondering if it's prime all the time. I think it might be prime all the time, but what if it wasn't? Is there a way that I could guarantee that n squared minus 3n plus 43 was a composite number, so that it had a factor, a prime factor times some other prime factor? If I can write it as a product of two numbers, and one of them's prime and the other one's not, or I can write it as a product of two numbers and one of them is not 1, that's enough for us to say that this is a composite number. So you might ask yourself, how can I construct a composite number of the form n squared minus 3n plus 43? And my thought was, okay, I could factor this if n squared and negative 3n and 43 had a factor in common. So you might say, okay, well, how will all three of those terms have a factor in common? Well, they would have to have a factor in common again with 43, but 43 is a prime number. So you say, just let n equal 43. Then n squared has a factor of 43, and negative 3n has a factor of 43. And of course, 43 has a factor of 43. So you could factor out the 43 from this term and this term and this term. Kind of like you're factoring out an x, but instead you're factoring out a 43. And you'd say to yourself, well, 43 times 43 gives me this first expression, and 43 times negative 3 gives me the second one, and 43 times 1 gives me the last one. This expression in the parentheses simplifies to 41. So we end up with 43 times 41, which is 1,763, composite. It is the product of two prime numbers, 43 and 41. Neither one of those is 1. So the question is n squared minus 3n plus 43 prime for all positive integers n? No, it's not. because here's my counter example. When n is equal to 43, it's composite. So we found a composite value for that expression, so the statement is false. Now, this is still not deductive reasoning, but at least it's more insightful than that other brute force method where we were just plugging in values for n. The other method, we were just saying, that's prime, that's prime, that's prime. But I mean, we really weren't even getting any pattern out of it. I mean, you could see that the prime values were increasing, but you say, okay, so what? What is that? You know, that's not going to tell me anything about whether or not the next result is composite. The key to our argument here, or the key to proving that this was false, was thinking about how this expression might be written as a product of two numbers, one of them not equal to 1. And, or alternatively, the way I'm thinking about it is, how can I make these three terms have a common factor? Well, since the last number is 43, they'll all have a common factor if n is equal to 43. So that's one way of doing it. So again, deductive reasoning is about thinking for yourself. It's about thinking critically. And it's not just thinking critically by looking at evidence, because that's critical thinking as well. This is thinking critically and using the rules of logic to come up with some airtight conclusion that we are absolutely certain is true, provided our initial assumptions are true. That has to be true. The axioms or the assumptions that we make at the beginning must be true. And of course, our reasoning has to be sound. The way we get from A to B must follow the rules of logic, which we can learn through studying this book, The Transition to Advanced Mathematics. But this is how mathematicians think. This is the essence of math. People think that math is all about numbers, and I mean, to some extent it is. They think that this is just about calculating things. It's not about calculation. It's really about understanding underlying patterns in these mathematical structures, which are composed of mathematical objects, and seeing how all the pieces fit together, and then also what are the implications of those pieces. And I find it really beautiful as you prove a result and you prove a result and you prove a different result. What you end up with is this beautiful mosaic of ideas. And it's very abstract and it can apply to a lot of different things. But that reasoning that leads to that result is called this deductive reasoning. And I think the results that you end up with are really beautiful. And I'm not the only math person who feels that way. So here are more specific reasons to study pure mathematics. I'm just going to get rid of my little video here. I'll just read this quote to you. Oops, sorry. This is one of my favorite quotes, excuse me. It says, "A mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they are made with ideas." And that's really what we're doing, is we're finding these beautiful patterns. And our patterns are lovely and often can be represented geometrically. And we see a lot of that in these images here, which I actually found online on a website that was talking about the golden ratio. So they were showing us the golden ratio in nature and how beautiful it is in all of these 6 images. So yes, sometimes the patterns are not made of ideas. Sometimes it's some beautiful spatial object or some beautiful object in the plane, or some sort of some object that you could imagine that's similar or analogous, excuse me, in hyperspace. All of that is math. And of course, even though he is making a comparison to painters and poets, and please know that I have enormous respect for painters and poets. My entire family paints except for me, and I love poetry. Um, what I love about this quote is that it says that math is like poetry, and for me it is. I love math for math's sake. Um, I like applications as well. I think applications are really cool, but it is the logic and the reasoning and the beautiful proofs and the beautiful results that I find so satisfying. Again, there's this idea that we get to be correct forever, which is kind of nice. And then this one is kind of funny. Maybe we don't want to be like Emperor Palpatine, but the fact that we get to be correct forever might make us feel like we have unlimited power. No, our power isn't unlimited. Our power is somewhat limited with deductive reasoning. But what's pretty cool is that you get to be right a lot, and that's nice. But again, getting back to more reasons why we might want to study this. Here's a great quote by Bertrand Russell. It says, "Pure mathematics is a subject in which we do not know what we're talking about or whether what we're saying is true." And I think that's so funny. He's saying that in the sense that we really don't care about the details of the mathematical objects that we're studying. What we care about is how those objects are related to each other and the overarching mathematical structure that relates those objects to each other. So again, using the example from abstract algebra, when you know something is a field, you know all of the things that all of the things that you've learned about fields apply to that thing, apply to that set of objects. So it doesn't matter that you're talking about real numbers or polynomials or some other matrices or something like that. If you know that those objects form a particular structure, like a ring or a field or a group, for example, then you get all of the conclusions about rings, fields, and groups for free, because you understand the structure, you understand how the objects themselves interact with each other. So the details of exactly what it is we're talking about are not the thing. That's not the interest. Our interest is really about getting rid of all of those details and focusing on how these objects interact with each other and how they behave. And I think that that's really interesting. The second part of the statement is kind of funny as well. This is much more humble than that other statement that we're always true. Here he says that pure mathematics is a subject in which we don't know what we're talking about or whether what we're saying is true. And yes and no. We know that the thing that we're proving is absolutely true for all time, provided our axioms are correct, provided that the foundation that we started with is absolutely true. But we're not actually proving that the foundation is true. We're not exploring the axioms. We're exploring the implications of those axioms. So this is a much more humble statement that says, just because I'm able to prove all the logical implications of something doesn't necessarily mean I know the truth. I only know what would have to be true if what I thought was true is true. And I won't go into that any further. I'll just read this quote from the Nagel and Newman book on Gödel's proof to you as one last thought on rigorous abstraction. This is mathematics is the land of rigorous abstraction. He says, or they say, a land of rigorous abstraction, empty of all familiar landmarks, is certainly not easy to get around in. But it offers compensations in the form of a new freedom of movement and fresh vistas. So we have freedom there. We're not restricted by details. The intensified formulation of mathematics emancipated men's minds from the restrictions of customary interpretations of expressions placed on the construction of novel systems of postulates. So we don't have to worry about, again, the details of what something actually is. We're just focusing on how it behaves. And as the meanings of certain terms become more general, their use became broader, and inferences that could be drawn from them are less confined. So what this is saying is, because of the abstraction, in some sense, what we're saying does not apply to a particular thing. But in another sense, it applies to everything that matches that pattern. Since what we're saying now does not just apply to a particular collection of objects, it doesn't just apply to real numbers or natural numbers or complex numbers or sets of polynomials or sets of matrices, but instead applies to all of the objects that have a particular structure, all of the sets of objects that have a particular structure. Now we're able to take something that is very general, and it tells us about the relationships between things, and we're allowed to apply it to everything. I think the simplest example, or one of the simplest examples that I often use, is the example from calculus, the optimization problems. As Calculus 1 students learn to find minimum values and maximum values of some function y equals f of x, they're finding the maximum and minimum values, relative minimums and relative maximums, or maxima and minima, as well as absolute, what are called extrema, minima and maxima. You're learning how to do that for a particular class of functions, and they're the functions that we study in pre-calculus. So you're able to find mins and maxes. If students say, well, what is this for though? Like, what does f of x represent? The answer is it could represent anything, any function of a single variable that you want to optimize. If it has a form, it has a closed form expression, a mathematical model that represents that function, represents whatever it is we're trying to measure. Maybe we're trying to maximize or minimize area, maximize or minimize volume. Maybe we're trying to make something as aerodynamic as possible. Let's see. Of course, all of the applications to business, a profit, you want to maximize your profit. You don't want to minimize your profit. You want to minimize your cost. You don't want to maximize it. You want to maximize your revenue. But I guess it would be more important to maximize your profit than it would be to maximize your revenue, right? Revenue is just your income. We want to maximize your income minus your costs, so that the money that's going out in order to run a business. But those are just 5 simple examples that you can just think of, or 6 simple examples off the top of your head of functions, which can often be written in terms of one variable that you might want to optimize. So when you're in Calculus 1, you're learning how to optimize y equals f of x. You might feel like you're just learning how to optimize this sort of random object. You're like, why would I ever do that? Well, because f of x could be anything, any function that can be represented that way. We can now find minimum values and maximum values. And how useful is that? So applied math is using math for those purposes, using math for those ends, and trying to come up with appropriate mathematical models to describe our world. And that's very satisfying, very interesting. But pure math is coming up with how to maximize or minimize that function that we started with, just in general. Like, let's make it as general as possible. So that's why you should learn to prove things. This is the end of my talk. Thanks for staying. If you hung in there, that's great. See you next time.